Welcome back to 6th grade science. Today's video is the start of a new unit. We are doing energy, focus, and motion for the next 5 weeks. To start that discussion, we are going to begin with objects in motion today. What's motion? Is it when I move my hands? Is it when I do this? Is it this race car flying down the track right now?
Begin launch sequence.
Go.
T-minus 7, 6, 5, 4, 3, 2, 1. Go.
Yes. Technically, motion is just a change in position. So every time I move my mouth to talk, my mouth is changing position, my mouth is in motion. You sitting at home watching this video, if you follow my finger here to here, your eyes are moving and therefore it's a change in position and it's motion. Now, motion being a change in position, what is position? Well, position's a location. So consider this point A, where my finger is now. When I move it, it's now at point B. So that's a change in location, therefore a change in position. A frame of reference is something that's not moving with respect to an observer that can be used to detect motion. What do I mean by this? We're going to use riding the bus or any other vehicle as an example for a frame of reference. So when you're sitting in the seat, whether it's a bus seat or a car seat, you don't feel like you're moving, and yet everything outside the window is moving. The reality is that you're what's moving and they're not, but because you're using them as the frame of reference, to you, they're what's considered moving because they're going from point A to point B. So when you're traveling in a bus or in a car, you are going a distance. So what is a distance? Technically speaking, distance is the length between 2 points. More specifically, the length of the route between 2 points. So if any of you have done the 100-meter dash in gym, your distance is 100 meters. It's how far you've traveled from point A to point B. The SI unit for distance is the meter. Now in the United States, we refer to miles and miles per hour, but other countries like Canada use kilometers or kilometers per hour. If you've ever looked at a speedometer, you might see 2 sets of numbers. The first set is miles per hour, and then the second set is kilometers per hour. Now, that's how many miles or how many kilometers you would travel in that hour at that constant speed. But Mr. Morgan, you just said that the SI unit is meters. A kilometer is different, isn't it? Not exactly. Different prefixes are used to change the unit. You can have something known as a centimeter, which you see on rulers. This is a very small version of a meter. So instead of saying point blah 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 for your meter, you would just say 1 centimeter. You can also, instead of going smaller, you can go bigger, and that's where kilometers come in. So 1 kilometer is equal to 1,000 meters. So instead of saying I'm going 1,000 meters per hour, you would just say I'm going 1 kilometer per hour. So depending on if you're going bigger or smaller, you will use a different prefix. And this is not specific to meters. We haven't covered it much, but different prefixes are used throughout science in general to show the size of something. So if I'm going to go a really short distance, I would use centimeters to measure, or if I'm going a really long distance, I would use kilometers to measure. And again, there are different versions, so if you're going to go really, really, really far, you can use something bigger than a kilometer, or if you're going to go really, really small, you can use something less than a centimeter. Something that can be used to measure distance is a map. And I'm not talking about, well, I guess I kind of am talking about the maps you have on your iPad or your phone or different things. But what I'm specifically referencing here is a paper map. How can you measure using a paper map if it's not a ruler, it doesn't tell you anything? Maps have a scale on them, and it can be seen here. It's usually a little bar, and it tells you that that length on the map is equal to that distance in real life. These scales are used to measure points on the map, or the distance between 2 points on the map. So if I want to go from New Berlin to South New Berlin, I can use the scale on the map to determine how many miles it is. What's another important component of motion? Direction. So with motion in general, it's just going in one direction, but you don't know what direction it is, therefore you don't know what way the motion's occurring. You have your relative directions, and relative are kind of vague directions. So for example, up, down, in, out, left, right, forward, backwards, or sideways. Those are all examples of relative directions. You also have your cardinal directions. These are your specific ones. You have north, south, east, and west. On maps, you have a compass rose, which is seen here, and this compass rose tells you the directions relative to the map. Directions are important because they tell people where to go. If I was giving you directions to the school, I couldn't just say, go 3 miles from New Berlin. Okay, 3 miles in what direction? Do I go 3 miles south, 3 miles north, 3 miles east, 3 miles west? You could end up somewhere totally different than intended just because I didn't provide the direction that you're supposed to go. So with direction, I want to talk about vectors. Vectors are a measurement that has both size, in this instance it's distance, and motion. Now they're typically represented with an arrow. The arrow shows you the size, and in this specific instance it's the distance, and the point of the arrow shows you the direction that it's going. All right, let's talk about speed. What is it? It's how fast or slow something is moving. This determines how far you're going to travel in a given amount of time. So if I'm going 100 miles per hour, I'm going to travel 100 miles within that hour. Or if I am traveling at 2 centimeters per second, every second I'm going to go another 2 centimeters. Speed involves distance and time. So the SI unit is meters per second, or in the instance like I used with America, miles per hour. Now how do you calculate speed? Average speed is calculated by taking the total amount of distance and dividing it by the total length of time. Now, earlier when we were talking about different types of energy and electricity, with the different formulas, you could calculate different components depending on what you had. So using the formula for speed, if I know distance and time, I can calculate speed. If I know time and speed, I can calculate distance. And if I know speed and distance, I can calculate time. Speed is constant. And what do I mean? Because right now my hand's moving really fast, whereas I slow it down and it's moving a lot slower. So that's not constant. By increasing my speed here and decreasing it, that's my instantaneous speed. So that's that speed at that moment. But when I am traveling, let's say 60 miles per hour, and that is the speed I'm staying at, that speed is always constant. So 60 miles per hour is always 60 miles per hour. But when you're traveling in a car, you go through towns, you have traffic, all different things slow you down or cause you to speed up. So your speeds vary in the sense that, okay, at 1 second you're going 50 miles per hour, and then the next thing you know, you're going 51 miles per hour or 52 miles per hour. So speed is constant in the sense that when you're traveling at 52 miles per hour, it will always be 52 miles per hour. But that doesn't mean it stays there. The instantaneous speeds, which remember is the sudden change from fast to slow or slow to fast, or change in speed in general, is a lot harder to calculate than the average speed. So now we talked about motion, we talked about direction, we've talked about speed. Speed and direction together gives you velocity. Technically speaking, it's the measure of speed and direction, so it's both combined. Just like direction was a vector, velocity is also a vector. So if I had an arrow like this one representing velocity as a vector, the length of the arrow would represent the speed, and the point of the arrow would represent the direction that it's going. So the SI unit for velocity is very similar to that of the SI unit of speed. Remember, the SI unit for speed is meters per second. Well, the SI unit for velocity is also meters per second, except it also has the addition of direction. So that's how it's different. If it's just meters per second, all that is telling you the speed. But if your end result gives you meters per second north, meters per second south, meters per second left, meters per second in any direction, that is the SI unit for velocity. It has to have both. Objects can have the same velocity. So if you and I are both traveling from my classroom to the bathrooms at 1 meter per second, we are traveling at the same speed and in the same direction. Therefore, we have the same velocity. If you're traveling downstairs from the stairwell by the Commons towards Miss Cameron's room, and I'm going from my room towards the bathrooms, and we're both traveling at 1 meter per second, we're traveling at the same speed. Do we have the same velocity? No. And the reason is we're heading in different directions. So while we're at the same speed, our directions are different, therefore it's not the same velocity. Now let's say we are racing down the hall, and we both leave from my room at the same time frame. And I am going 5 meters per second, and you're going 3 meters per second. We're heading in the same direction, but we're going at different speeds. Do we have the same velocity? No, because you're traveling at a different speed than I am, even though we're heading in the same direction. So remember, in order to have the same velocity, you have to be traveling in the same direction at the same speed. Average velocity is calculated almost identical to speed. And this makes sense if you think about the units. So the units of speed are meters per second, and the units of velocity are meters per second plus distance. So to calculate it, velocity equals distance over time. But Mr. Morgan, that's the same formula. Yes, but remember, with velocity you have a direction. So mathematically, you can calculate it the same way, you just add the direction to it. It only works for velocity if the direction is included in the answer. All right, next up we have acceleration. Acceleration is the change of velocity in a moving object. More specifically, it measures the rate of change of velocity. Just like velocity was a vector, this is also a vector. So typically when you hear the word acceleration, what do you think of? Because I think of acceleration, I think of either pressing on the gas pedal on a car and increasing my speed, or taking off running and increasing my speed as I do that. Acceleration is an increase in speed, but it's also a decrease in speed. Now how does that work? How can it be an increase in speed and a decrease in speed? Well, remember, acceleration is just the measure of a change in velocity. So you can have a positive change, which would be an increase in speed, or you can have a negative change, which would be a decrease in speed. When you have a decrease in speed, it's a negative acceleration, also known as deceleration. Now, acceleration can also be a change in direction without a change in speed. So it can get a little confusing there. But remember, velocity is made up of speed and distance and direction. So if you change speed or you change direction, you're changing the acceleration, but not if you change both. Now, if you're in a car and someone pushes on the gas pedal really quick, you might notice that you kind of lean back a little bit. That is you feeling the acceleration. Or if someone takes a turn in a car and you kind of move with the car in the turn, you're in your seat, you're either going left or right, forward, backward, that is you feeling the change in acceleration. So how do we calculate acceleration? Well, when calculating the acceleration, direction isn't changing. So mathematically, acceleration is equal to the change in velocity divided by the change in time. So to figure this out, I would say I started at 0 miles per hour, or 0 meters per second. And then I increased my speed to 5 miles per hour, or 5 meters per second. Now, I'm using the same numbers just to make it easier, but 5 miles per hour is not equivalent to 5 meters per second. And this change occurs over a total of 2 seconds. So to figure this out, I'm going to take my end number and subtract it from my beginning number. So I started at 0 miles per hour and I ended at 5 miles per hour, or 0 meters per second, 5 meters per second. So I'm going to take 5, my end number, and subtract 0, which is my initial number. 5 minus 0 is 5. And then I'm going to divide it by the total amount of time, so the length of time. So time-wise, I'm starting at 0 seconds, and I'm ending at 2 seconds. So I'm going to take 2 minus 0, which is 2. So for this calculation, I would take 5 divided by 2, and therefore my acceleration is 2.5. But 2.5 what? Well, the SI unit for velocity is meters per second plus a direction, and the SI unit for time is seconds. So the SI unit for acceleration is meters per second squared. As always, if you have any questions, please reach out to your teacher, whether that's Miss Cameron or myself. Bye.